I didn't know what I was going to talk about here. So when I said I would come, or getting close to the date, I was working on a new project on malaria, and I thought I would talk about malaria. That work didn't quite move as quickly as I had hoped. And then I thought, okay, I'll do some work I've done on the oceans. And then I said to Simon, I don't know what to do. I was planning to do malaria, but then I thought I'd do the oceans, but then I watched the talks before, and he said, well, actually, I was hoping you'd talk about climate change. So I put together a talk on climate change. And actually, I think it'll fit in nicely with following Karina and also setting up Professor Dixit, because it relates to both these papers. This is the only real data I'm going to show you. These are parts per million of CO2 in the atmosphere measured from Mauna Loa in Hawaii. So that's the squiggly red line, or the black line is looking at the annual average. And the green line shows when the negotiations began. Now, it's a little bit like the slide we saw before on water pollution. It's hard to know. You don't have the counterfactual, so we don't know whether the negotiations really helped a lot, because the slope of that curve would have really shot up right when the green line appeared. But I think it's probably pretty safe to say that the negotiations have had very, very, very little effect on the thing we really care about, which is climate change caused by the increase in greenhouse gases. Well, I'd like to understand, why is that? Why have we failed to do that? It seems to me one of the most striking things about all environmental issues is that they're self-inflicted problems. So there's something about us, and how do we control ourselves? How do we get our acts together, which is really an issue about institutions more than anything. So this is what I want to understand, the actual climate negotiations. And I look at them as a game. So let's think of a card game, and in this game, everyone's going to get 2 cards. One's red and one's black, and you get €5 if you keep your red card, plus you get €1 for every red card handed in, and then which card would you hand in? I've played this game hundreds of times, literally, and the result is always the same in a qualitative sense. This is very consistent with Karina was saying. This is a public goods game, and roughly in the neighborhood of half, but always between 1/3 and 2/3 of the people will contribute, but not everyone contributes. Now this picture, which the idea of this came from Tom Schelling, how to draw this, if I do this correctly, yeah. So this is what the others are doing. So this is a game in which you have 100 people playing. This is the payoff if you contribute your red card. Oops. And this is the payoff if you keep your red card. And so these are the numbers I showed you before. And this is assuming that everyone else hands in their red card. If you hand in your red card, you get €100. If you keep your red card, you get 104. The main point is that no matter what others are doing, the payoff to you of keeping your red card is always higher than handing your red card in. So self-interest, if that were your motivation, and you weren't an altruist, or should I say you weren't Norwegian, then what you'd expect to happen is there'd be a tendency for people to hold on to the red cards, and you end up down here. This is called a Nash equilibrium, and the payoff for everyone would be €5. But if the group cooperated effectively, you'd be up here, everyone would hand in the red cards, and the payoff would be €100. So basically, if you think about a problem like climate change, it's how to get the world from here, and there'll be a tendency for the world to go here, up to here. That's the challenge, which is a big challenge. Karina mentioned how people play, and this is actually an illustration of that. In this particular game, you could either hand in your red card or you could keep your red card, and we're playing this game with 5 people. This work and the other experimental work I'm going to show you is all done with a co-author, Astrid Dannenberg, from the University of Kassel in Germany. And what you see is when the game starts, the contributions are pretty high. 4 out of 5 people are handing in their red card. and then it declines as the game is playing. This is exactly what Karina said happens. Then when you start again, you have a thing called a rebound effect. It goes up a little bit. That's because hope, hope triumph over experience. And, but then it comes down again. And then just a little bit of hope at the very end. One person thought, okay, let's give it a go. And then it collapses. By the time you get to the last round, no one even tries. This, for me, is the best illustration I know of the history of climate negotiations starting in 1990. Well, that's not quite the game that we're playing with climate change. The first treaty on climate, the Framework Convention on Climate Change, Article 2, says that the ultimate objective, this is the collective goal that countries have agreed on, is that we should avoid dangerous interference in the climate system, which is implying that there's a kind of a red line, and if you're on one side of the red line, it's not dangerous. Maybe it's safe, and on the other side of the red line, it is dangerous. So the question is, if that's the game, would people play differently? Well, here's a representation. I'm just doing this so I can show it in the same kind of pictorial way. Again, you have here, this is for a game played by 10 people. This is actually a game I played with Astrid. This is what the number of others that contribute. This is 15 chips. So now you're playing not with cards, but with poker chips. And you are given an endowment of chips, and you have to decide how many to hand in. You're given 10 black chips, each person in this group, and those are worth 10 cents each. And then you're given 10 red chips, and they're worth €1 each. So the red chips you can think of as being a more costly form of reducing emissions compared to the black chips. And the payoff that you get is 5 cents for every chip contributed, whether it's red or black, minus €15 unless at least 150 chips are contributed in total. So you've got a threshold at 150 chips. And if at least 150 chips are contributed, you get to keep your €15. But if 149 or fewer chips are contributed, you lose the €15. And this is not the same game we saw before. This is called a coordination game. So what happens here is if no one else contributes and you contribute 15 chips, you're going to get a payoff of minus 10. We give them extra amount of money, so they're never out of pocket. So no worries about that. And again, the payoff will increase because as more chips are contributed, you and all the other players all do better. But what happens here that's different from the previous game is that when you get to this level where everyone else is giving 15 chips, this is almost like John List's idea of being pivotal. You now are in the position, taking as given what others are doing. If you contribute 15 chips, there are 10 of you in total, you will now ensure that you avoid the threshold, the dangerous threshold. And then your payoff jumps up because you got that extra €15. So given that the others have contributed 15 chips, 9 others, your best choice is to contribute 15 chips. And now you still have a Nash equilibrium on the left side, which is the bad one. But now there's another one on the right side, which is a good one. And what causes this to happen is not any kind of design issue. It's that there's the real prospect in this game. It's an actual prospect of a catastrophic threshold. So if we were playing this game with a catastrophic threshold, this should really change how people play. And as it turns out, and you might think that people would still want a free ride here, but actually, as it turns out, the results are completely different than you would ever find in a classic public goods game experiment. And what happens here is half the players contributed exactly 15 chips, but the average was 15.1. So it's almost perfect. It's quite stunning. And these were with groups of 10. I think your experiment was with 3. 10's quite large. We were warned that people would never do this, but they did. People will do this. So now you can have some, Chris, you can have some optimism now, and your optimism is being rewarded. We see virtuous behavior in the laboratory. Did I do something? Let's see. Can I? Okay. So basically what's happening here is that the incentive to coordinate is very, very strong. 15 is also a clear focal point. So it's in many ways not surprising that the players did well. So the point is, if this were the game we were playing, I think humans would do a much better job. It's not the game we're playing because we have uncertainty. So one source of uncertainty is where is the tipping point? And if you read the literature on science, there's actually a lot of uncertainty about that. Another one is what happens when you cross the tipping point. And I should mention that this is the only place where economics really enters. This is a purely scientific phenomenon. Where is the tipping point? Both of these are uncertain, and the question is, does uncertainty matter? Well, I wrote a pretty simple theoretical paper on this that had very powerful conclusions. Uncertainty about the impact, this model predicts, should have zero effect on behavior, none at all. Uncertainty about the threshold should be crucial, and in particular, if you had certainty about the threshold, you would have a coordination game, and you would expect international negotiations to succeed. If you have uncertainty about the threshold, you would have a prisoner's dilemma, and you'd expect the negotiations to fail. So to test this, and this is what the theory shows, you want to test this in the lab. Is the theory any good or not? So instead of taking the threshold to be 150, we now keep the expected value at 150, but have uncertainty between 100 and 200. So the distribution here is a uniform distribution. It's different than the one Avinash is going to use. And then we also have uncertainty about the impact. Instead of it being 15, that was the price you would pay for the catastrophe, as it were, it's between 10 and 20, same expected value. And what happens is, okay, let me just explain this. We're doing 10 groups, and there are 10 people in each group. This is certainty about both the impact and the threshold. This is certainty about the threshold, but uncertainty about the impact. So in both these cases, you have certainty about the threshold. Here you have uncertainty about the threshold. Here you have uncertainty about the threshold and certainty about the impact, and here you've got uncertainty about both. Now, if the theory were right, these two bars should look the same. These two bars should look the same, and this pair should look very different. So basically, the theory does very well. In these cases here, 18 out of 20 groups avoid catastrophe. Now, you might say, and the model predicts, they all avoid catastrophe. Well, you might say, okay, well, 2 out of 20 didn't do so well, which I think is a pretty good record. We're talking about humans, after all. Okay. So what happened is, in each of these groups, there's just one person who didn't conform, as it were, didn't do the right thing, told everyone that he or she was, maybe it's a he. I don't know what you were thinking, Kathy. Maybe it was a he. Said that he would contribute around 15 and then contributed 0, the free rider. So a liar and a free rider. But I'm very sure that person would have suffered a lot for playing that way. And I'm very sure if we played this again, which we didn't, that behavior would have changed. So it's really quite amazing how consistent this is. And over here, virtually every group achieved a catastrophe with probability of 100%. And this is basically what I think is going on in the climate negotiations. We talk a lot about uncertainty about the impacts, but actually the most important thing is on the science side. And unfortunately, this problem is uncertain. Now, there's another dimension of this, and I learned this from Steve Carpenter. In fact, I learned a lot of my ideas I'm applying here to all my years involved at the Baer Institute. But one of the issues that ecologists have looked into include early warning signals of whether you're getting near a regime shift in nature. And so what we did is the theory I developed also makes predictions about how big the uncertainty has to be to tip human behavior, where it moves from being a coordination situation, which again humans are good at dealing with, to being a prisoner's dilemma, free riding kind of situation. And what the theory predicts is so on the left side here, so now you've got uncertainty on the horizontal axis. Here you got certainty, so 0 uncertainty as it were, and now you're widening out the distribution of the uniform distribution. So you're getting a lot of uncertainty here. And what the theory predicts is, as long as uncertainty is very small, the players will coordinate, and you'll follow this full cooperative outcome, which is the best you can do for the group. But that once you get past this dividing line, you get this collapse, and behavior should flip, and then you would get non-cooperation, much more like the first picture I showed you in the presentation. So this is what the theory predicts, and then we went into the lab and wanted to see if this was true or not. And I make a lot of bets with my co-author, Astrid. The only one I remember is the only one I won, which was this one. And she didn't think that the behavior would change right at that line, but actually it did. So this is what happened. These are, in the blue and green, you're seeing proposals and pledges by the players. So this is words, what they're saying they're going to do. and in the green and the yellow. In the blue, you're seeing actual behavior. So you see that they track very well on coordination here, but then when they get to the dividing line, the contributions collapse. Now you might say, well, that's a lot higher than down here, but what you have to understand is that the chips, these chips here in this gray shaded area are very, very cheap. So the sacrifice that people are making right here, what number? 5, okay. The sacrifice people are making here is very, very tiny. It's 50 cents. So these are not real altruists. And in fact, there's quite a substantial amount of collapse in cooperation that occurs right at the threshold. And what happened then was that catastrophe was virtually certain. So unfortunately, the one reason the climate change problem is so difficult is that Mother Nature hasn't quite cooperated with us, that this is an experiment that hasn't been done before, and we don't know exactly what's going to happen. So we need to think about strategies for how to design the negotiations. And one was adopted in Paris in late 2015. And a lot of people think that the Paris Agreement was a great success. The main reason Paris is a great success, every country in the world agrees that climate change is a big problem and has made pledges to address it. Of course, there's one country now that has had second thoughts, but I'm sure that'll be just a temporary blip. But the main reason Paris was successful is that it's a voluntary agreement. So you make a pledge for how much you're willing to do, and if you don't do it, there's no clear consequence. The only innovation in Paris is that there's a kind of a framework in which countries can name and shame one another. So if a country makes a pledge that others think is too small, they can speak up. If they don't fulfill their pledge, they could be some kind of ostracism, I guess, some kind of critical comment. This is built into the agreement, although you could say that at least some of this was always there in the process. In any event, would that approach work? If you look at the Framework Convention Secretariat's analysis, this is actual emissions. These are projections based on the pledges that have been made, and this is where their analysis, this is based on the pledges that were made. And the blue curve here is what the world should be doing if it wants to stay within 2 degrees C, which was the announced group goal. This is what the world has to do in 2030 if it's to stay within that goal with a probability of 50%. So basically, the agreement's having virtually no effect on the trend at all. And in order to have even a 50% chance of meeting the group goal, you would have to have basically what I call a miracle occur right here, where this long historical trend is just going to suddenly change. What they're assuming here, by the way, is that countries are going to fulfill their pledges, and that's not so clear. Well, we go into the laboratory, we did an experiment where we looked at this naming and shaming arrangement, and basically what we found is that the arrangement changes what the players say. It doesn't change what they do. And think about it. We've seen Paris, it changed what they said. We'll have to wait and see if it changes what they do. The last thing I wanted to mention was what other strategies can we pursue? Bill Nordhaus of Yale University has an idea that is exciting and provocative, and that's that countries would form clubs. Now, actually, this is a little bit like Karina's idea, that there are these maybe like-minded or like altruistic people, and they would have formed their own group. The problem with a problem like climate change is that this is a global public good, and in a sense, you can't really choose your own group. But Bill's got this idea, well, let's choose a group and have that group set a carbon tax and then impose tariffs on imports from non-members of the group. And he's trying to see whether you can get some leverage from cooperation on trade to apply it to climate. And he solves this, it's a paper based on simulation, and he solves it using something he calls an evolutionary algorithm. I'm looking into this just now with Astrid, and in fact, she gave me some new results this morning. And we have a simple model I'll try to explain in the next minute or so. This is Bill's results, and what he finds is for a low tax, carbon tax, and these are the possible, this is the number of countries participating and in the climate agreement, and these are the different tariff levels. So 0 over here, 1%, 2%, and up to 10%. And these, again, are the tax levels. And the U.S., under the Obama administration, thought that the social cost of carbon is right around this neighborhood here, just to give you a sense. I guess the new administration puts the value a little bit to the left of that. And what you find is that if you have a low tax, you're going to have full cooperation with this approach. But as the tax gets higher, it gets harder and harder to enforce the agreement by linking it to trade. And by the time you get to a carbon tax about of $100, the best you can do is you've got some countries in the agreement and some out at a very high tariff level. That's actually a very bad situation in a way because you don't have full cooperation on climate, and now you have trade wars as well. One of the assumptions he makes, I'm just about done. One of the assumptions he makes is that there can't be any retaliation. Well, it turns out if you have a model that can explain why there's cooperation on trade, it is virtually certain that there would be retaliation. So we modeled this. This is the theory. So this is very much like the picture you saw before. This is cooperation on climate change. And I've added in here all the cooperation on trade because it's in this trade model I have, it's virtually guaranteed you're going to get cooperation. So this is if you don't link the two agreements. So basically what it means is you have success on trade and failure on climate. If you link them, the game changes. So this is a strategic choice. Do you link or not? And then the game changes, and you end up with another coordination game. So that's the Nash equilibrium. This is another one. This one's better. So you want to see whether linkage would be a good thing. Potentially it is here. Now, Bill solves his model using this evolutionary algorithm. I'm more interested in how real people would behave, and so Esther and I go into the lab. That's the work we're doing right now. And I'll just show you one result. And this treatment, the countries can decide independently whether they want to impose tariffs or not. We did this with 19 groups. We had one group didn't. We had one no-show, so we had to drop one. And what you find is if they choose, so initially they have to play the voluntary game. So these pictures look very much like the ones I showed you before. Remember the first one I showed you? Then after that, they can vote whether they want to switch and link what we'll call the climate game with the trade game. And you'll see here, this group chose not a single person wanted to switch. So they kept doing the same thing over and over and over again, getting the same basic result. There were other groups that switched, and you can see like this one here, and then they coordinated perfectly. Okay, so now the trade linkage works really well, and you also see that in some other groups. So there's some success here, but then there were groups where it didn't succeed. Here they finally switched to try the linkage, but you see they did really poorly. They didn't coordinate very well, and that also happened down here and here. So what you learn from this is that the linkage offers the promise of some assistance. I have to tell you that there's a very restricted set of parameters where this could be true. So this is not the solution to climate change. Even in Bill's analysis, it's not, but when you take into account the likelihood of retaliation, it's really constrained. But on top of that, then you have to ask, will people do the right thing? And even here, we're finding that there's a lot of sensitivity, even if you adopt more interesting institutions than I have here. That's it. Thanks very much.